In this video, we are going to be looking at ray diagrams with lenses. So how can we trace particular principal rays so that we can predict information about the image that a lens forms? So first, we need to become familiar with the thin lens approximation. In the last video, we saw that the convergence or the divergence of light rays through a lens was due to the fact that there were two refractions. One that occurred when the light entered the lens, and then a second refraction when the light left the lens. So that's what's actually happening. With the thin lens approximation, we are instead going to pretend that there's only one refraction, not two. So we're going to use this approximation from now on. And instead of two refractions, one when the light enters the lens, one when it leaves, we're going to look at just the one principal axis, or one axis that runs through the center of the lens, and pretend that the refraction happens there. So that's the idea behind the thin lens. Pretend there's one refraction, but we're keeping in the back of our mind there really are two refractions because the light both enters and leaves the lens. All right, ray diagrams for convex lenses. Very similar to ray diagrams for spherical mirrors. Some subtle differences that are worth knowing. The most obvious difference, and you can already see it on the screen, is that unlike spherical mirrors, which only have one focal point, lenses have two focal points. And that's because light can pass through in either direction through a lens. So you get a focal point on both sides of your lens. Here we have a candle as our object, and we are going to be looking at three principal light rays that are leaving that flame. Of course, light is going in all directions, but three principal rays are enough to tell us where the lens will form an image. So there we go, thin lens approximation. Pretend all of the refractions happen just at that axis. Principal rays, let's do it. Principal ray number one, it leaves the candle parallel to the principal axis, and then it refracts and bends such that it passes through the focal point on the opposite side. This is our converging lens. We know the light rays are going to converge. Principal ray number two. This principal ray passes through the focal point on the same side of the lens. So it passes through that left focal point, not the rightward focal point. And then it refracts such that it leaves parallel to the principal axis. Now that's enough, but we should learn one more ray for good measure. Light that passes through the center of the lens is going to go unchanged through that lens. So overall, this is where our light rays meet. So that is where this lens will form an image. There we go. There's our three principal rays. You should be familiar with how to draw ray diagrams for lenses. That's our image. Now, lost art of image description here. The location is that we are beyond the focal point on the opposite side of the lens. That's where the image is located. Orientation, size, and type are the other things that we need to deal with. Orientation, this is an inverted image. It's upside down. It's on the other side of the principal axis. This is a smaller, not by much, but it is a smaller image. If you were to measure it, it is smaller than the actual object. As a real image, a reminder, a real image is when your light rays actually converge at another point. And we've seen this before, but now I want to put it in the context of lenses. The result of this diagram on the previous slide is we have our object, the candle there. We have our convex lens, and that convex lens will converge all of the light rays. And if we put a screen at the right point, we're going to be able to focus an image of the candle on the screen. And our ray diagram told us that that image would be inverted, that it would be smaller, and that it would be real. So that's the result of doing this experiment in real life. All right, let's draw another ray diagram, a second example. This one is for a concave lens that caves in. This is our diverging lens where the light rays spread out. Similar but slightly different rules, and it's worth noting the differences. All right, so thin lens approximation, we're going to pretend there's only one refraction. Principal rays for concave lenses. First one, We're going to look at a ray that's parallel to the principal axis, and it is going to refract in such a way that it diverges through a line that includes the same side focal point. What do I mean by that? I mean, imagine a line that goes through the same side focal point. That is the line along which this ray will diverge. So the last example with the converging lens, this parallel ray went this way through the focal point to converge, whereas the parallel ray through this concave lens, it needs to spread out, so it can't go down through this focal point, so it's got to be along a line through the other one. So it's got to go through the focal point that lets it convert, or that lets it spread out and diverge. Principal ray number 2, this is the one that's going to pass through the far side focal point. We have to use both focal points. It's a good way to say this. So we are now going to be using the focal point that we have not yet used, which is the one that's on the far side. And the light ray that's going along that line, once it hits our lens, is going to refract in such a way that it leaves parallel to the principal axis. All right, last but not least, the ray that goes through the center will go through unchanged. It is helpful to draw this ray, even though you don't technically need it, because if all 3 of your light rays don't intersect at the same point, then you know you made a mistake. So this is a useful third ray to use as a check to make sure that it also has the same image location as the first 2. So we have a diverging ray example. Just like with the diverging mirror, we have a diverging ray. We need to trace back all of the spreading out light rays to a point where our dumb monkey brains are going to think that those refracted rays are coming from. And if we trace the red one back, we trace the purple one back, we trace the yellow, I couldn't think of the word yellow, the yellow one back, we see that they all would trace back to a point of intersection there. So that is where our image forms. That's our image. Again, there's nothing actually there. We couldn't project that image onto a screen because it is virtual, but our eyes would see something because they would see these 3 rays on this side of the lens, and our brain's going to try and make sense of it. And so our brain's saying, oh, this is what the rays look like? Well, they must be coming from this point, and that's why we see an image. Let's do a little lost art of image description to end things here. Our image is between the lens and F, the focal point, and is on the same side of the lens as the object. Orientation, size, and type are the other things we need to hit. The orientation is upright. We notice that it is upright relative to our object. The size is smaller. And the type is virtual. The light rays diverged. They didn't intersect. We had to trace them back to a fictional point of intersection. There we go. There's our ray diagrams for lenses, lost art of image description. We'll do some practice in class.